Mr. Jim Lipman from
Okay.
Sidense.
Thank you very much, Sean. And thank you all in the audience for spending some of your valuable DAC time with me. And I'm sure the giveaway at the end of this has absolutely nothing to do with it. But what I'm going to do, I'm going to spend a few minutes describing what we call the smart connected universe at Sidense. Some people will refer to it after I describe it as IoT on steroids, and you'll see why. I'll then talk about how devices and applications in the smart connected universe have very stringent memory requirements. I'll give you an example of where our particular product, 1T OTP memory, fits in. And at the very end, firmly tongue-in-cheek, I will explain where we're going to be going with the smart connected universe. So let's start the journey. Just a few words about Sidense for those of you who do not know who we are. Okay, well worth doing this then. We've been around about 10 years. Last year was the 10-year anniversary. We've been a trusted memory partner for that length of time. Privately owned. We have 65 plus employees, 80% of them in engineering. Well resourced. And we financially are doing very well. Last year was our best year financially, last fiscal year, and we have a 45% cumulative annual growth rate over the last 3 years. So Sidense has been around a while, and we will continue to be around. So what is this smart connected universe? Well, smart because it encompasses compute power. And connected because a lot of things are connected, mostly on a wireless basis. It goes over a number of more well-known market segments. We have mobile communication and mobile computing. We lump them together under computing. IoT, automotive, industrial, wearables, and medical. And after I'm finished, you might say, well, there's a lot of overlap. But if you listen to different people's definitions of IoT, everybody has their own definition of what's in there, too. So we're just going along with the crowd. But this, for our particular purposes, because the memory required shares a lot of common attributes across all these market segments. Low cost, security, reliability, and so on. And we'll go into more details about each of those as I go along as well. So let's dissect what's inside the smart connected universe. And this is similar to what many of you have seen before. If we look at three particular pieces of the smart connected universe, which also are applicable to IoT, you have edge nodes, hub nodes, and compute nodes. Edge nodes on the left are what senses the environment, body functions, and the like. It can be smart devices, can be dumb devices, the sensors, but it gathers data. And that's what the D stands for, detection. Then we have S for smart. A lot of these sensors actually have compute power within them. So, hello. So we're able to do some computing before we take the data and aggregate it into the hub nodes. C stands for communication. Information from the edge nodes go to a hub node. The data is aggregated. More compute power might be used. And then that is transmitted to more sophisticated compute nodes, usually in the cloud. And the compute nodes analyze the data and make decisions. Basically, they're actuators. And the action they take depends on the information they get. Now, S could also stand for security, which is becoming far more important in the smart connected universe. What you have here is you have to have security on the edge nodes, because any edge node that can be hacked, being on the network, means that any other node on the network can be hacked as well. And if you notice, the S for smart and for security gets bigger as you go from left to right. It becomes more important. Edge nodes can be very simple, very low cost, on the order of a few cents for a temperature sensor. And if you go to the right, you can have compute nodes that are very sophisticated server systems that cost millions of dollars. So the money invested increases dramatically as you head from edge nodes through hub nodes to compute nodes. Now, we talk about the different pieces of smart connected. You have communication, you have security, you have conditioning of the edge nodes. There's a lot of different memory technologies available. This chart discusses a number of the embedded ones, which I want to concentrate on. The horizontal cycle is the endurance of the memory, how often you can rewrite a particular bit in the memory. The vertical is the cost associated going higher as you move down the vertical scale. So we have mask ROM, two types of OTP, eFuse, floating gate MTP, and eFlash. Now each of the pies has up to 4 different segments. And those 4 segments have security, field programmability, low power, and temperature range, because each of these memory technologies is very good or very bad at some of these. If we look at mask ROM, it's an inexpensive technology. It's low cost. It's easily done, but it's fixed, meaning once you have it, you can't change it. If you want to change the contents of a ROM, you go through another cycle in fab, and that costs money, or it may delay your product significantly. If we look at eFlash, very high endurance. This is for data that you need to write over and over again. And you notice it's very field programmable, of course, but the security is a little suspect because it's easy to ascertain the contents of flash memory. Power is low, but it's expensive because it requires more math steps. So that's why it's on the bottom of the chart where the dollars are increasing. If we look at floating gate MTP, similar to flash, but the endurance isn't quite as high, and yes, it also requires different additional processing steps and additional masks. eFuse, temperature range very good. Problems? Not very secure. Very easy to find out if a fuse has been blown or not. In addition, very large area compared to the other competing non-volatile memory embedded technology. So it's expensive and limited to a relatively low number of bits, a few thousand. There are 2 types of OTP, floating gate and anti-fuse, and I'll spend most of the time talking about anti-fuse OTP, one-time programmable, because that's what Sidense does. A lot of benefits, works over a wide temperature range, a very secure technology, very difficult to hack or change the contents. A program bit is irreversible, very low power, and of course it's field programmable. Now just jumping eFuses again for a second, they're not really field programmable. So there are some ways to do it, but it's very difficult. So predominantly, once you have an eFuse that's, you know, the way you think you're going to want it, you're not going to be able to change it. Okay, let's look at the Sidense 1T OTP, one transistor OTP memory bit cell. You program it. Well, I'll start on the right, describe the diagram. This is what we call a split channel architecture. You have one gate and thin and thick oxide below the gate. You program it by putting a sufficiently high voltage on the gate to blow the oxide underneath the thin gate region, the channel of the transistor. When you blow it, you cannot unblow it. You can't unring the bell. It's a program bit. The programming is very accurate, very reproducible, and very, very difficult to detect, either visually or by scanning techniques, because charge storage is not involved in the setting of a bit. So it's very reliably programmed. It requires no additional masks or process steps, a standard CMOS process. We have silicon all the way from 180 down to FinFET nodes and very wide industry adoption.
And some cameras, and we had a different recorder.
Typical architecture for our OTP macros has three main pieces. You have the memory array itself, the integrated power supply, and both of these are hard macros. And then you have controller logic, which is a soft macro. Now the OTP memory array, different configurations, different ways of setting it up, also contains things such as sense amps, muxes, a little bit of control, things like that. The integrated power supply supplies voltages for the memory array needed for reading and programming the bits, derived from chip voltages. If you don't need it, you can program the bit from an external source. There are different pieces of the integrated power supply, charge pumps and other things that you can use. So the user has a lot of flexibility of how he can use the power to be able to work with the OTP memory array. The controller controls things such as testing, error correction, and things along those lines. And again, there are different pieces of that you can use or not use that give you flexibility when you want to insert the 1T OTP macro in an SoC and control its operation there. Now in Smart Connected, I mentioned that we have a lot of memory alternatives, but OTP in Smart Connected has a lot of advantages. You can use it as an alternative for things like, as I mentioned, eFuse, mask ROM, flash. You use it for things like analog trimming and calibration, configuration, storage, secure and otherwise, device identification. So OTP and different devices in the Smart Connected universe perform a lot of different functions. Now, let me give one example, a smartphone. The typical smartphone has over 20 instances of OTP. One of the organizations that does teardowns, Tech Insight, took apart an iPhone 6 Plus and found that the bill of materials was almost $250, of which almost half is silicon. And what were those pieces of silicon doing? There were 25 different chips on the main board in the iPhone 6 Plus, and they were doing all these kind of, they were doing all these, all the functions you see on the left, plus probably a few more I haven't included. So OTP finds a lot of uses in the Smart Connected device realm. Now, the demands on memory in the Smart Connected universe are many. And I don't have time to talk about all of them there, but I want to concentrate on two. I want to concentrate on security and specialty processes. Security features. I mentioned that anti-fuse OTP is very difficult to reverse engineer by deprocessing, scanning, and other techniques that people use. So it's very difficult for a hacker to get in and do something with it. This is very important because one of the analyst organizations back in early January wrote an article saying that somebody had hacked into thousands of consumer devices, including many smart TVs and even a refrigerator, created a botnet that sent out 750,000 malicious emails to individuals and enterprises. As I mentioned before, any device on the network that can be hacked means any other device can also be compromised on that network. So having physical attack resistance because of the nature of the architecture of the 1T OTP, the split channel, is very important. In addition, you have tamper resistance in a lot of ways. There are various read modes that can be used. Differential, single-ended, redundant, and redundant differential. Differential, for example, negates the possibility of having power signature analysis. And if you look down the list here, there are many, many different things that we put into our memory arrays to defeat hacker attempts to get in and compromise those particular arrays. Now, specialty process support. Like IoT, Smart Connected does not depend solely on leading edge processes. They run the gamut from 180 nanometers or even above in some cases all the way down to the new FinFET technologies. We have available at Sidense a number of macros that have been proven in a variety of specialty processes, high voltage, BCD, RF, and the like. We support over 11 different process nodes of the specialty type and have 55 customers using our devices for those specialties. And they're used for things like touchscreen controllers, display drivers, power switching, PMICs, power management ICs, and the like. The advantage of using our 1T OTP is much smaller than alternatives, and you have auto grade available up to 150 degrees centigrade, which means they can be used for under the hood auto applications as well as harsh industrial applications. So this is an important part of addressing memory in the smart connected universe. In summary, smart connected to us are the next big things. It spans a whole variety of different market segments that are very important and very rapidly growing. OTP is a very good, secure, and reliable replacement for other types of non-volatile memory technologies, as I've explained in the presentation. And we bring design as some real advantages with the 1T OTP architecture that we have compared to some competing solutions. So where are we going with Smart Connected? Okay, sometimes truth is stranger than fiction. Remember the Rogue refrigerator? That could happen to you. So, thank you very much for joining me. I appreciate your time. Check us out on our website or IP or on the Chip Estimate website. Use our IP in your next great chip. Stay and talk with me and my colleague, who I'm going to introduce in a second, because I'd like you to possibly chat with him later on because he has something interesting, and enjoy your visit to DAC. Waldeck over there is our CTO, and he has put together a model of a FinFET transistor with a 3D printer that he would be happy to show anybody on the side after you do your stuff.
Oh, yeah, absolutely. So talking about FinFET,
yes,
and it's a very, very popular topic here at DAC. Does 1T OTP work with FinFET?
Absolutely.
Oh.
We have basically the same architecture all the way down from 180 down to FinFET. FinFET has a lot of advantages over planar technology, has better performance than planar at 20 or 28 nanometers. I'm talking about 16 nanometer FinFET right now. Leakage is approximately a factor of 10 lower. And the read margins between programmed and unprogrammed cells is much better. So yes, we operate very well in the FinFET world.
Can you erase bits that have been programmed in 1T OTP?
I'm glad you asked that, Sean.
I feel like Johnny Carson. I did not know that.
You cannot erase bits. They are one-time programmable, but we have what we call emulated MTP, emulated multi-time programmable, meaning if you're going to be doing few-time programmable or redoing encryption keys or code segments, you use a memory that's bigger than the one you need initially. You have uncommitted segments within the memory, and then you write into them as you go along. It works very well, and many of our customers use the emulated MTP on their particular chips.
All right.